recording is set up. Yeah, recording is set up already, so we can start. Okay. So last time we actually talked about the idea of the A star of the heuristic function and also the A star search. Okay. So the core idea of the A star search is that we use the overall estimated cost, overall estimated path cost to prioritize the node for further expansion. Okay, so no matter you are working with what kinds of tree search algorithm, the overall structure of the general tree search algorithm is the same. Okay. So all the search algorithm we list out here, they all are following the same underlying code base. Okay, they are using the same overall code base shown here to conduct the search. The major differences is what kinds of data structure is used as the fringe for prioritizing which node for expansion first. Okay, so each time in the general tree search algorithm, we select a node for expansion, and the node is selected by the underlying principle, underlying mechanism, or the data structure used to be the fringe. And when we are working with A star search, we actually want to take this consideration. Okay, so essentially the search tree itself can be considered as the search tree itself can be considered as a collection of paths that your algorithm have been searching so far. Okay, so as you can see here in the previous example, we have right here the search tree. Oh, no, but this one's fine. Okay. So as you can see here, when we are taking a look on the Pythagoras, this node, the Pythagoras node is representing a path from Arec to Cebu to Pythagoras. Okay, and the ODS, this node is actually representing a path from Arec to Cebu to ODS. Okay, so you can see that the search tree itself is a collection of paths. Okay, and each node is actually representing one path. Okay, so we can consider the selection of the search tree for expansion in two perspectives. You can consider we are selecting a terminal node in the search tree and we try to build a bigger search tree. Or you can consider the moment we are selecting a terminal node, we are actually selecting a path for further expansion. And when we're talking about expansion, we are talking about adding one node to the path. Okay, so given any node, okay, given the node at the terminal side, okay, if there is 5 neighbors, then I can attach 5 different combinations, 5 different possible next nodes to the path and generate 5 paths. Okay, so the moment you are growing the search tree, you are actually trying to generate more paths. And the overall idea is that as long as you keep on generating the path, you eventually can generate a path that can reach the goal state. Okay, so the search algorithm is kind of exhaustive exhaustive brute force in nature. Okay, but in the A star search, we introduce one key component, that is we have a heuristic function that can estimate given any node the cost needed to take to get to the goal state, okay? So by using that estimation, combining with the terminal node's original path cost, I can actually calculate the overall estimated cost starting from the initial state to the goal state. Okay? Okay. So the major differences of the A-star search and the best first search is that in the best first search, we prioritize the node completely based on the heuristics. Okay. But in the A-star search, we are actually taking the best of both worlds. We have a component that is real path cost. And we have another component that is heuristics. By combining the heuristics and the real path cost component, we can get an overall estimated cost starting from initial state to the goal state for a particular terminal node. And for each terminal node, I can do a calculation like this. Then after I do a calculation like this, then I select the route that have the least cost. Okay. The idea is that for all the terminal here, they all represent a path from the initial state to that terminal node. But selecting what path for expansion, we take that path combined with the heuristics to estimate the overall potential path cost estimated to get from initial state to the goal state. For each path, we do that, okay? And after we do that, we can actually estimate which path is likely to get faster to the goal state, to get to the goal state with a least cost, okay? And then we select that path for expansion. And essentially, when we are talking about selecting a path, we are also talking about selecting a terminal node. So that is the mechanism of selecting terminal node in the A-star search. Okay. So any questions? Any questions? Any questions? So if you really feel difficult understanding it, just remember your search tree will keep on updating the path cost of each node when you add a node into the search tree. And as long as you keep track on the path cost of each node, and you get that node, and then you put it to the heuristic function, and then you get the heuristic value, take the path cost plus the heuristic value, then you get the priority value for selecting the node for expansion. Simple as that. Okay? If you don't remember the essence of A-star search, just remember this. Okay? Essentially, when you are building a search tree, we'll keep track the path cost of each node. Okay? And selecting a node under A-star search is that you take all terminal and then you take the path cost plus the heuristic of that node. Okay, then you get the value for prioritizing the node for expansion. Okay, and you order them. Okay, and the node with the lowest cost, you select it and then expand. Okay, simple as that. Okay, so I understand that you may not fully understand the A-star search, but at least I hope you can understand the rules involved. Okay, it's actually that simple. Okay, as long as you are able to keep track the path cost in the whole search tree, then you can do the uniform cost search and you can also do the A-star search. Simple as that. Okay, simple as that. Okay. So let's take one thing that you must remember is that A-star search only A-star search is only optimal when the heuristic is admissible. Okay, that is A-star search is proven, mathematically proven to be optimal, to be able to search the shortest path only if the heuristic is admissible, meaning that you do not overestimate the cost. Okay. Okay. You try to predict the cost always lower than the real cost. Okay, then that is called admissible heuristics. Okay, the term admissible heuristics means that you try to predict the real cost to be smaller than the real cost. Okay, you try to predict the cost with a value smaller than the real cost. Okay, your prediction can never be bigger than the real thing. Okay, and taking a look on the shortest on our heuristics, the heuristic we use for this example is the straight line distance to between any node to Bucharest, between any node to the goal state. Okay, and we know mathematically the shortest distance between two locations is the straight line distance. So no matter what route you are taking, the straight line distance must always be shorter than that route. Okay? So in that sense, the straight line distance is a admissible heuristic. Okay? Because it is always shorter than any path. Okay? So the straight line distance between two locations should always be the shortest when compared to any path between two locations. Okay, this is fact. Okay, this is fact. Okay, so this is mathematically proven to be true. Okay, so we can be sure that the moment we use the single line distance to solve our Lomini Turing problem, the straight line distance is a heuristic. Okay, is a admissible heuristics. Okay, you need to remember the word admissible. Admissible always means the estimating the cost to be smaller than it actually is. Okay, you need to remember this. Okay, and let's take a look on an A-star search example. So now we come across with this example again. Here we start at Cebu, okay, and the straight line distance to Bucharest table is shown here. So this table become our heuristic function. And here at the bottom, we have the priority queue. So we start at Cebu. Cebu is actually our initial state. Okay, so it have the path cost of 0, and according to the heuristic function, the straight line distance of Cebu to Bucharest is 253. So 0 plus 253 equals 253. So as a result, we add Cebu with 253 value into the priority queue, and we add a node there, and we add the root node there. Okay, and then we expand the Cebu node. Okay, so the Cebu going to mutual WeChat is 80, and Cebu to going to Fagres is 99. Okay, so the Fagres node here has a path cost of 99. Okay, have a path cost of 99, and according to a straight line distance to Bucharest, it have a heuristic of 178. So as I already tell you, the rule of doing the A-star search is that I take the path cost and I add it with the heuristics. Okay, the path cost according to the search tree is 99 for Fagres, and then for the straight line distance to Bucharest table, the Bucharest have a heuristic value of 178. So we add these two values together, and it becomes 277. And we can do the same for the mutual WeChat as well. According to the search tree here, the path cost is mutual WeChat is 80. Okay, because Cebu going to mutual WeChat is 80. Okay, and then mutual WeChat, according to this heuristic function table, heuristic value is 193. Okay, 193. So we add the path cost, and we add the path cost, and we also add the heuristic value. So it becomes 273. So this is why we'll write 273 right here. Okay, and then we add the two logs to the priority queue according to the value. Okay, and because we mutual WeChat have a smaller value, so next time we will expand it first. Okay. Okay. So when we expand with mutual reacher, so now we have two nodes, okay? Because according to the network here, we mutual reacher going to p-test T and we mutual reacher pointing to Canberra, so we have two nodes, okay? And according to the A star search tree, okay, the p-test T here have a path cost of 80 plus 97, 80 plus 97. When we are talking about the path cost of a node in the search tree, we are talking about the cost from the initial state, that is the root node, to that node, okay? So many students actually would take the 97 as the path cost, but this is not true. It should be 97 plus 80. Then that will be the real path cost of the p-test T. Okay, and 97 plus 80 equal to 177. Okay, so that is why we have 177 here. Okay, and I have already told you that A star search runs in this rule. Okay, you need to take the path cost and you add it to the heuristic when in the according to heuristic function. And here the heuristic function is given to you as a table, and we see p-test T, and we go look at the table. P-test T have a value of 98 as the heuristic value. So we take 98 this value, put it here. So the heuristic value is 98 combined with the path cost we calculated before, that is 177. 177 plus 98 equals to 275. Okay, so this is how it works. Okay, similar to Canberra, you get 80 plus 176, then it becomes 236. Okay, 236 is the path cost of Canberra, because when we are counting the path cost of Canberra, we need to count it from Cebu. And if you travel from Cebu to this Canberra node, it need to go this way and this way. So the cost is 80 plus 176. So the path cost of the Canberra is 236. Okay? Okay? It is still following the same logic of calculating the path cost. Okay? And you should never take 178 as the path cost of Canberra. You should not take the path cost of 146. You should not take the path cost of 146 as the path cost of Canberra, okay? Because the path cost here means the cost taken from Cebu to Canberra, okay? The Cebu from the path cost from Cebu to Canberra, okay? And the cost is 80 plus 146, so it's 236. Okay, that is the path cost, and the heuristic cost can be taken here. So we add these two values here, and that becomes 386. Okay, 386. So we add the p-test T and the Canberra to the priority queue. And because p-test T have a smaller path cost than Factorless, so we'll put the p-test T before the Factorless. Okay. And the Canberra have a path cost bigger, have a priority bigger than the Factorless, so we'll put it behind it. Okay. So because p-test T have a smaller value, there is more priority value than the Factorless, so it will be put before Factorless. Okay. And Canberra have a bigger priority value than Factorless, so we'll put Canberra behind Factorless. Okay. So any questions? You can see that when we are running the A star search, we are running it in a very mechanical approach. Okay, you just follow the rules, repeatedly do it, then you can always get the correct answer. Okay, even though you may not understand the principles of the A star search, you just repeat the rule, that you will get the job done. Okay. Yeah. So now we expand p-test T, okay, and then we have Canberra, and then we have Bucharest, because according to the graph there, p-test T is going to Canberra and p-test T is also going to Bucharest. Okay, so let's dissect it again. Okay, when we are talking about the path cost, we are talking about the cost from the root node to that particular terminal node. So for this Canberra node at the bottom here, the path cost will be 80 plus 97 plus 138. Okay, The reason why is that for the agent from Cebu to get to this Kevlar node, it need to go through this route, and this route. Okay, so the path should be 80 plus 97 plus 138. Okay, we are just again following the same principle, same rule when we are calculating the path cost here. So using this rule, we can calculate the path cost of Kevlar as 350. Okay, I don't do the real calculation. I don't do the real calculation here. Okay, you just trust me. You just take the trust me flow approach on this. Okay. Okay. Because it's too time consuming to open up the calculator. Okay. You just trust me that 80 plus 97 plus 138 equals to 315. Okay. You just trust me on that. Okay. And if you go to see the heuristic function table, Kevlar has a heuristic value of 160. So you take 160 and then you plus 315, then you get 475. Okay, 475. Okay, so 475 is the ultimate priority value for the Kevlar. Okay, or the overall estimated path cost of Kevlar. Okay. And we can do the same for Bucharest as well. And the path cost of Bucharest is 80 plus 97 plus 101. As you can see here, it takes the agent to go from here to here, and to here to get to Bucharest. So from Cebu to Remedial Richa is 80. From Remedial Richa to Pitești is 97. And from Pitești to Bucharest is 101. So we add these three numbers together, and this is the path cost of Bucharest. Okay, this is the path cost of Bucharest. Okay, and the heuristic of the Bucharest is 0 because you already at the goal state, so the heuristic is of course 0. Okay, it takes 0 to get from A to A, right? Okay, so the heuristic is of course 0. So adding up together is 278. Okay, and we add these two new nodes to the priority queue, and we found that the Bucharest is after the Fabulous because it has a slightly bigger value than Fabulous. Okay, and Kevlar is having 475, so it is at the end. Okay, and you may find that the priority queue is having two Kevlar, and that's normal because that two Kevlar is referring to two Kevlar nodes in the search tree. Okay, so it is normal. And of course, the Fabulous is being expanded because it has the lowest priority value. So we found that the Fabulous only have one route to Bucharest. Okay, and we use the same technique. Cebu to get we add the Bucharest node here, and for this Bucharest node, it takes from Cebu to go to Fabulous to go to Bucharest. Okay, from Cebu to Fabulous to Bucharest. Okay, so the path cost of this Bucharest node should be 99 plus 211. Okay, and trust me, that should be 310. Okay, you can also use your calculator right now. If you have one to evaluate by calculation, it should be correct. Okay, so you can see no matter what node we are working on, the path cost of the node should be counted from the root node. Okay, here the Bucharest path cost is 310 because it takes to go to this Bucharest node at the left hand side from Cebu to Fabulous to Bucharest. So the path cost of the step cost of Cebu to Fabulous is 99, and the step cost of Fabulous to Bucharest is 211. Adding these two numbers together, that becomes 310, and that will be the path cost of the Bucharest node. Okay, so you should always remember the path cost of a node should be the overall sum of the step cost from the root node to that terminal node. Okay, you cannot just give me the step cost to get to the node as the path cost. That is wrong. Okay, that is wrong. Okay, because the reason why I emphasize this so much is because I see many students making this error during assignment and exams in previous cohort of the student, okay? I have seen many students in the past, in the several past 1 to 2 cohort of students, they often make these mistakes. Okay, so please remember, do not make these mistakes. Okay, path course of the node means the overall sum of the step course from the root node to that node. Okay, you cannot just take one step course and call it the path course unless you are talking about the first layer node. Okay, okay. But anyway, so no matter what, your path course should be the step course or from the root node to the node. Okay, just because this Fagran's node and the Remedial Region node is one step from the CBOO, so it looks like that the step course is the path course. Okay.
So in A-star search, the path course is the sum of the step course plus estimated.
Yeah. So in the A-star, what I would say is in the A-star search, we take a look on the overall estimated cost. And the overall estimated cost has two components. The first component is the path cost, and the second component is the estimated cost. Okay, so yeah, as you can see here, you can see the formula right here. Okay, you just add them all together. Okay, and then because this Bucharest node is 310, so we add it right here, okay, between the two calculus in the priority queue. Okay, so next time we'll expand the Bucharest node. Because the Bucharest with the cost of 278 is the smallest cost node. Okay, so we expand it, and because it is the goal state, so it stop right here. Okay, so we stop right here. Okay. And after we find the goal state, then we do the backtracking. We go from the Bucharest to the p-test, and we go from the p-test to Remedial Region, and we go from Remedial Region to CBOO. Okay, so we get Bucharest, p-test, Remedial Region, CBOO. Okay, and we take this list and we flip it backwards. Okay, they become CBOO, Remedial Region, p-test, and Bucharest. Okay, so this is how you find the ultimate solution for the agent to go from the initial state to the goal state. Okay, but of course we are humans, we can skip that backwards part. We can just eyeball identify that, okay, it goes from CBOO to Remedial Region to p-test and to Bucharest. Okay, so we can eyeball it. Okay, but computers cannot eyeball it. You need to do some backtracking. Okay. And for the detailed backtracking code, you can take a look on the codes I released on the Moodle. Okay, I've already written the code for demonstrating backtracking actions. And it is already available as the source code I given it to you in the Moodle. Okay, if you are interested, you can take a look. Okay, but the idea is not that difficult. Okay, but because those are specific implementations or of the algorithm, and I believe that most of you have learned their structure and especially learn about linked list, so you should already know the overall idea of how to do it already. So I just skip talking about it right here. Okay, so any questions? So even though you don't understand A-star search, you only memorize two rules. For every node in the terminal node, to get the path course, you count from the initial state, you count from root node to that node, and you get all the step values, add them together, that becomes a path course. And after you get the path course, you add the heuristic value, and that overall value becomes the priority value you use for selecting node for expansion next. Okay. And then each time when you need to select a node for expansion, you select the node with the lowest priority value. Okay. You remember these two rules, then you can construct the A-star search. Okay. So any questions? Any questions? So I believe that it is far more easier after I illustrated the fact that to run the A-star search, you just need to remember two rules. Okay, and that's it. Okay. So I already talked about the optimal part. You for the A-star search to be optimal, to be able to always select the shortest path, you must make sure that the heuristic value is admissible. Okay. In fact, you can take a special. You can think about this. Okay. If all the heuristic value is 0, then it becomes uniform call search. Right?
All right, because you always plus 0, which yeah.
So in fact, you can consider uniform call search as a special case of the A-star search, where all the heuristic value is 0. Okay. Technically speaking, A-star search requires the heuristic value is admissible. Admissible means you always get the heuristic value smaller than actual value.
Smaller or equal to or smaller?
Smaller or equal is fine.
Okay.
So let's think about this. Okay. Let's think about this. If it is smaller than the actual value, then technically speaking, 0 is more than any value. If all the value is positive, if all the step cost is positive, all the path cost is positive. All the path cost is positive means that taking 0 as the heuristic is smaller than any value. It's smaller than any path cost, right? So taking heuristic equal to 0, it is a heuristic that is always admissible, although it means nothing. Although it is not practical. Okay. Okay. So you can kind of consider the uniform call search as a special case of the A-star search, with that's theoretically correct but not quite make sense heuristics of everything is 0. Okay, because in heuristics, the heuristic that define that if the cost should be smaller than actual value, technically speaking, 0 is smaller than all values, right? So if you have a heuristic value that is equal to 0 no matter what, technically speaking, that is a admissible heuristic, right? According to the definition here, okay? And if you take that heuristic and put it into A-star search, then you actually reduce the A-star search as a uniform call search. So you can consider the uniform call search as a special case of the A-star search. Okay, makes sense, right?
Yeah.
So this is some extra observation that I want you to take a look at. Okay. So I hope everyone will be able to finish to be able to better understand how the A-star search is being executed. Even you don't know the core idea, just remembering those two rules is enough for you to at least dry run the algorithm. Okay. Okay. So now let's talk about search beyond classical searching. Okay. So let's think about this. In some situations, you will want to find the configuration of something. Okay, you want to find the configuration of something that is optimal. Okay. For example, considering that for example, you are now the product manager of Apple. Okay, assuming you are now the product manager of Apple. Okay, so you are required, you are given a task to make an iPhone, that is targeted market price is about $4,000. Okay, 4,000 Hong Kong dollars is the target price. You need to figure out a configuration of iPhone that the production cost is minimized and the profit margin is maximized. Yeah, so optimization problem. Okay. So essentially, in those kind of problems, it is not quite different from the search problem we have been talking about. In the previous search problem we have been talking about, we want to find a route from the initial state to the goal state. Okay? But now we don't care about how to get from the initial state to the goal state. We only care about finding a state that have the optimal objective value. Okay? Okay. So you may think about this. When we are talk last, I believe that in the one to two lectures before, we actually talk about the equine problem. In the equine problem, you have a chessboard and you need to place different different queen chess pieces that they do not kill each other. Okay, so in this problem, in all our implementation, we actually don't quite care about the action that is taken to get to the goal state. What we care about is what is the goal state. Okay. So we actually know about the properties of the goal state, but we don't know exactly what is the goal state. We can describe what we want for the goal state, but we don't know exactly what is the goal state.
So you want, it's like, we know the goal state is x comma y.
Yeah.
So we find, 1, 2 is the goal state.
Yeah. Yeah. So something like this, okay? So our target is to find the exact goal state given a bunch of constraints that we have established, okay? In those problems, we actually don't quite care about what is happening behind the hood of getting good in between what action has been done to get to the goal state. We only care about the goal state. Okay, so in those problems, and one major differences here is that when we are talking about the old style traditional search tree, we stop right at the moment we get to the goal state. Okay, but in the foreign algorithm we talk about, we don't stop at a particular goal state. We rather want to if possible, exhaustively, if possible, we want to start a state that have the maximum objective value. Okay. So in fact, we are transiting from one kind of agent to another agent. So if you recall in the lecture 2, we actually talk about this. Right to now, when we are talking about the the traditional search algorithm, we are talking about the goal-based agent. Okay. Now we don't talk about the goal-based agent anymore. We talk about the utility-based agent. Okay. We don't measure whether we reach the goal state by defining the goal state. We define a value that describes how close we are to achieve our objective. And we want to find a state that we can achieve our objective the most. Okay. See, just like the iPhone example I just talked about, we want to find a configuration or a state of the iPhone that can optimize the profit. Okay. Okay. And at the end, Apple, what Apple have done is in the past is the iPhone SE. They try to minimize the cost by selecting the using the old version of the shell of the enclosure, and they put in the best CPU, and the other things are keep the same. Okay. Then they have a thing. They have the state of the GPU to attract people to buy, and they use old parts so they can minimize the cost. Okay. And in real business, okay, you have many more factors that you need to take consideration on. Okay. So for the iPhone example, it seems very easy. I have you just have two factors, CPU config and the housing config. Okay, it seems very easy, but it is getting more and more difficult if you have more and more parameters that is being established, that need to be figured out. Okay, so we can consider all these factors to the combination of all these factors to be our state. Okay, and we are taking actions to keep on changing the value of the state or those factoring states, such that we can find a state that we can optimize our goal state, to optimize our objective. Okay. Okay. So I don't know if you have I believe I don't know if you have learned this in mathematics. No. Okay. No, not this one. Wait. No, no. Forget about it. Maybe our next time I will show it. Okay. So I don't suddenly remember how to draw it. Okay. So maybe I will talk about verbal. Okay? So you remember that in mathematics you may have learned that you have two functions and you try to find the optimal value that satisfy two different problems, two different equations.
Oh, linear program.
Yeah, linear program. Yeah, linear program. Okay. So this essentially what we are trying to do is something similar to linear programming. Okay. Or maybe I can find an example right here. Okay. Okay. So essentially, I believe that you have learned it. I believe that this is part of the curriculum in the DSE. Okay. You are given the two different functions, two different you are given the two different equation. Okay, and you need to find the you want to find the optimal value. Okay, in the space. Okay. Okay, and this is easy if you just have two different factors to need to consider. Okay, this is quite easy if you just have if the number of factors you need to consider is low. But if you have a lot of parameters you need to consider in your problem, then it is not as easy to solve it as the linear program. Okay. Okay. So we introduce a method to I know that you may think that it is quite a stupid method. Okay, we are introducing a method that you kind of allows you to exhaustively search it. Okay? So this is what we are trying to do in the following discussion. Okay, we are switching from the goal-based search agent to utility-based search agent. You are trying to create some programs, okay, that can solve problems like linear programming doing optimization. Okay. I hope you still remember your DSE mathematics. You should have done question like this, is to try to find optimal value that satisfy two different equations. Okay, linear programming, right? And essentially, we want to do it not by mathematics, but by letting the computer to search the solution. to search the solution. Okay, so this is what we really want to do. Okay, and the first approach is so-called hill climbing. Okay, there is a lot of coding involved, but we are not going to retest your programming in the exams. Okay, the coding here is just as illustrative purpose. Okay, originally I want to put pseudocode here. Okay, but most of you are more familiar with Python, so okay, just Python it is. Okay, but in fact I want to write pseudocode. Okay. So essentially what we are doing in the hill climbing algorithm is that we start from an initial state, and for that initial state, we try to find all its neighbors. Okay? Okay? And for all the neighbors, we choose a neighbor that can give us a highest objective value. Okay?
So is it like what we do in the FC, find all the vertex, pop.
Maybe, okay, I'm not quite sure what you're talking about. Essentially, you start from an initial point, okay, and then I check out all the points around the initial point that have the highest objective value, and then I move to that objective value. I move to that state, okay, and I move to that state, okay, and I repeatedly do it until I get to a point that point is having neighboring states that do not have a objective value bigger than the value I'm having right now. Okay. So you can consider I am actually climbing on a mountain. Okay. I'm actually climbing on a mountain. Okay. Maybe I will try to use PowerPoint. Okay. So you can imagine a scenario like this. Okay. So you can imagine the surface space is like this, okay? It is a triangle, okay? And then you are starting right here. Okay, so I'm starting right here, okay? So the neighbor that you have is this way or that way. Okay. And because you are right here, your neighbor is maybe I put a circle dot here, okay? So this is you, okay? Change it another color. So this is you right. This is your starting point right here. Okay. So you go you go to the left. You go to the left. Then your utility value will remain the same. Okay. Maybe I will add 2 more items. It will be faster if I use the whiteboard, but I believe that it is easier for you to read if I draw it into the PowerPoint. So I do it. Okay. So here is the objective value. Okay, so in this problem, what we are trying to do is to find the optimal value of x, is to find value of x that can make the objective value becomes the biggest. Okay, so this is the problem we are solving right now. And our initial state is right here, okay? Our initial state right here. So because we are only working on one value x, okay? So there is 2 possible ways we can go. We can go either left or we can go either right, okay? So if we go right, the point will go along the curve, so it will go right here, okay? If I go left, then it will go right here, okay? So it will go right, okay? Because the right gives a higher value, right? And it keeps on going and up to the top. Then when it is at the top, the going left or going right doesn't give it a higher value. So it will stop at there, okay? So we can stop the search. Okay? So this is what Hill-Cramer algorithm is trying to do. Simple as that. Okay. Okay, I'm not going to talk about the pseudocode. Okay. I'm just going to talk about with this animation. Okay. If this is good enough. So this is what Hill-Cramer algorithm suppose is trying to do. Simple as that. Okay. The algorithm is just a elaborated way of explaining this logic. But although the pseudocode seems to be very complicated, but at the end of the day, it is actually that simple. The principle is actually that simple. Okay. But of course, I am oversimplifying things. Okay, if you have more than one variable, then you have your geometry of the curve of the third space would be not a triangle but something else. Okay, okay, but you get the idea from here. Okay, okay. If I get more variables, then I'm just trying more possible labeling node. Okay. And then I get the utility value, okay? But the idea is the same. Okay. Given the choices of the label, I choose one that can give me a high value and keep on going until I get to the point that all the label cannot give me a higher value that I stop. So this is the same. This is the overall idea of the Hill-Cramer algorithm. So any questions? Any questions? Any questions? And don't worry, in your exams, okay, you would actually not need to do any real programming tasks. Okay. Okay, you don't need to write a program from scratch. Okay. So you don't need to really recite the Hill-Cramer algorithm coding here. Okay. But this algorithm, although it is simple, but it has a major issue. So let's talk about this. Maybe. Okay, so now imagine my drawing is bad, but you get the idea. Okay, so in this now this is the newly this is the new this is a new problem, and we have another state space. Okay, this is a curve like this. Okay, and our x is right here. Okay, so maybe not so maybe here. Okay, our state is right here. Okay, so because our state is right here, so it will try to move left, it will try to move right, because the moving right will give us a better objective value. But when it reach here, okay, then that is the real issue. It will get stuck. Okay, so going left here, the objective value will fall down. Going right, the objective value will fall down. So it will start right here. It doesn't go anywhere. But we know from the graph that the optimal value should be right here. Okay? So that is the issue about Hill-Cramer. It can get stuck to the local optimal. Okay? And when we are talking about search problem, when we see a area that the objective value have a pointy edge, have a point that is slightly bigger than anywhere else, then we call it as a local optimal. Okay, and in this situation shown here, clearly that we can get stuck in the local optimal when we are using Hill-Cramer algorithm, because this is the nature of the Hill-Cramer algorithm. It cannot escape from that. Okay, so any questions? Any questions? Any questions? Any questions? And you may find in the PPT, I set a statement. Okay, So essentially, you actually see that climbing average in fog with emission. So it said that you are climbing the mountain without a strong eyesight. The reason is that when you are doing all the decision whether you go left or go right, you are using the localized information. Okay, when the node is when I'm moving left or right here, when the algorithm is moving left or right here, the decision is done by the value right next to it. Okay, the agent can only have a sensation. Oops. Okay. Can only have a sensation like this. Okay, its eyesight is limited to here. Okay, it only sees the bigger circles region, but not anything else. Okay, as you can see here, this is the agent, and this is the eyesight of the agent. So it only sees the few points right next to it. Okay. So that is also the reason why it gets stuck at local optimal. If the agent knows that, okay, if the agent have a eyesight as good as this one, okay? If the agent have a eyesight as good as this one, okay? Then you know that, okay, I have a global optimal here, I should go there. Okay? So that is the reason why the PPT would describe this behavior as climbing the Everest being fog sight. Okay, with fog, with fake fog, okay? With a limited sight, okay, and that is the reason why you really have limited idea of what is happening in the environment. Okay, so any questions? Okay. And I also get another picture right here that demonstrates the idea, okay? And I already talked about it, is that the local optimal is a peak that is higher than the neighboring state, but lower than the global maximum, okay? And the hill climbing algorithm limitation is that if I get into local state, I get stuck, okay? And the next is so-called the stochastic hill climbing. Is that I start from a position, and each time I move, and each time when I move, I am moving in a kind of random way. Okay, that is, I have, like, for example, I can choose to move up as far as this, or I can move as low as this. Okay, but instead of each time I go as far as possible, I try to randomize my move and try to choose a move that I can move up, but not the move up the most. Okay. So this is so-called the hill climbing algorithm. Okay. So when you are doing the basic hill climbing algorithm, if my eyesight is this, okay. So from the algorithm perspective, I can move to here or I can move to here, right? So the basic hill climbing algorithm is that I will move here, okay, and that's it. For the basic hill climbing algorithm, I will always choose to move to a place that can maximize my gain in the objective value. So in this case, it will move right here, okay? But for the stochastic one, it will move to a places that can increase its value, but not essentially maximize the gain. Okay, so it may move here or move here or move here. Okay, as long as something it can increase its optimal value, increase its objective value a little bit, that it go for it. Okay, it do it random. Okay.
You mean it's randomly deciding the step size of X?
Yes. Yes. So it will so wait. So essentially it will get a bunch of actions, okay, that can go uphill and randomly choose one of them. Okay. Okay. And I would say in this manner is that it will assign probability on for each different gain or the movement. Okay, so one movement it has a bigger gain, then maybe I assign smaller value to it. Okay, and another movement I get a smaller gain, I assign bigger probability to it. Okay, so each time I am randomly selecting over a bunch of actions that can make me move up. Okay, I'm not always trying to move up the nodes. Okay, the second one is similar to the first one, but it is quite different. The second one is that over a bunch of action I can do, I randomly draw one until I get one that can make me move up. Okay, so for example, by random chance, I may move here, I move here, but now suddenly a movement make me move here. Okay, so I will take this one. Okay, so that is so-called the first, no, this one. The first choice hill climbing algorithm. Okay, this is so-called the first choice hill climbing algorithm. Okay, okay, that is some step may be good, some step may be bad. I randomly choose a step, and once I choose a step that can make me move up, I choose it. Okay. And the last one is actually the random restart hill climbing. So essentially I keep opening that. So each time I essentially just so each time instead of I start at a position at one random position, I repeatedly do the hill climbing, but not in one position. I run it from here and next time I run it from here, and maybe I run it from yeah. Okay. Each time I run a lot of hill climbing, but each time I give it a bit different start. Okay, maybe this time I start here, 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 this time I start here. Okay, I keep on randomizing my starting point, and I keep on repeatedly doing the hill climbing algorithm. The idea is that if I do enough randoming, then maybe I get to start my search right here. Okay, and I can get to the goal state. I get to the ideal state. I get to the goal optimal. Okay. Okay. The idea is similar to you are playing Dungeons and Dragons, but you are keeping rolling the dice until you get the attack points you want to kill the monster. Okay. Okay. If I need to really think of an analogy, that it will be you are playing Dungeons and Dragons. You want to kill a monster, so you keep on rolling the dice enough until you roll a dice, dice point that you can attack the monster. Okay, that is exactly it is exactly the similar idea. Okay. Okay, so random start hill climbing will always able to find the goal state, because you keep on rolling the dice, you eventually can roll a starting point that is very close to the goal to the global optimal, and you can get to the global optimal. Okay. Okay. So the next is simulated anyway. Okay. The idea is broadened from metal fabrication. Okay. So I don't know I don't know if you are if you will randomly watch YouTube videos, okay? But there is a competition in the West, okay? This is a TV show that is asking some amateur metal forging people interested in metal forging, and they will need to forge a sword or forge a knife in the TV show. Okay. So when you are working with metal, when you're making working with metal forging, okay, when you are making a metal knife, okay, you will need to heat it in order to harden a knife. The first way you need to do is to heat up the knife and then let it cool down slowly. Okay, let a knife cool down slowly, allow its molecular I will not say molecular, allow the metal atom to rearrange in a crystal structure better, so it can be stronger. Okay, so here in computer science, data science, we follow this idea. Okay, we follow this idea. In simulated annealing, each time when we are trying to get to a next stage, we try to intentionally make some bad move. Okay, we try to intentionally introduce some bad move. So the bad move will allow us to escape from the local optimum. Okay. So I will use the image to illustrate it first. Okay. So as you can see here, we want to this problem we will want to get to the global minimum. Okay? We want to get the minimum value. Okay. So here is the local optimal. Okay, local optimal. If we are running hill climbing, we will start right here. If we are running the hill climbing, we will stop right here, because at this positioning, moving left to right will increase the optimal value, and this problem requires us to get a smaller value. Okay, so of course it will start right here, but simulated annealing allow you to occasionally make some bad move, and the bad move will push you away from the local minimum, and you may be able to get to the local global max minimum. Okay. So this is the idea of the simulated annealing. We reintroduce errors. We reintroduce some bad move during the search, such that when it gets to the local minimum right here, it can escape. Okay. But the next question is, if it is already right very close to the global minimum, okay, echo base very annoying, it keep popping up the URL. So if the search is already very close to the global minimum, you of course don't want it to make a lot of bad move. Okay, you of course don't want it to make a lot of bad move. Okay, so the frequency of the bad move should not be a constant value. You should introduce more bad move in the beginning, and you should introduce less bad move at the end. Okay? If you have a lot of bad move at the end, then it will jump away from the global minimum as well.
Just make the power into a negative one. Right?
Yes. We get the idea, and the next thing what we need to do is to establish a function that can gradually reduce the frequency. Okay, so that is what simulated annealing really is about. We follow the idea that as temperature decrease, the metal crystal structure, the metal atom crystal structure becomes more and more aligned and less the order is less chaos into the search. We introduce more chaos, more bad move at the beginning, and we reduce the bad move or the chaos at the end. Okay, so that is what we call simulated annealing. Okay, we introduce a variable called temperature. Okay, the temperature will keep on decreasing as the search goes on. Okay, and if the temperature becomes zero, if the temperature becomes zero, the search has been running for a long time already, so we'll stop. Okay, and the next idea is that we randomly choose a neighbor. We randomly choose a next state available for exploration. And after we get the neighbor, we calculate the utility value of the neighbor versus our current state. Okay. And then we get the delta. Okay. If delta is larger than zero, if the next state is better than our current state, then we move to that state. Okay, if the next state is not better, is worse than the current state, then we try to create random value that is smaller than the expected by the E number, equal number, power of delta E of divided by T. Okay, the delta E is the differences of the current state and the next state utility value. Okay, divided by temperature, and then you use it as power on the Euclidean number, then you get the probability. If it is smaller than the probability value here, then you move to that state. Okay, okay, and you can refer to this chart. Okay, this chart is actually showing the value of E powered by delta E powered by delta E divided by T. Okay, versus the temperature. Okay, okay. So here this graph is showing the changes of this value against the temperature. Okay. So as you can see in this diagram, as T decrease, the probability threshold will also decrease. Okay, so as the probability threshold decrease, that means that the chances of making a bad move will also decrease as the temperature decrease. Okay, okay. So this is what you really need to know right here. Okay. Okay. So because you are taking this value as the threshold, okay? So if this value is very small, then randomly generate number that is more than it is very unlikely. So at that time, the chances of you able to move to bad move will be smaller. Okay. Okay. And for this value, the delta is negative. Okay, the delta is negative. And if the temperature is decreasing, that means that this value becomes more negative. Okay, and because this value is more and more negative, okay, this is a power value, right? This is a power value, right? So it will back closer to zero. Okay, so this is why if I plot the graph like this to show the relationship as the temperature decrease, the E powered by delta back delta E divided by T, this whole chunk of thing is decreasing. Okay, so as temperature decrease, the chances, the threshold of able to make a bad move also decrease. Okay. Okay.
But usually the horizontal axis usually is from smaller to bigger, right?
Yeah.
Then okay, let's say
when we are doing the simulated annealing, the temperature is starting up with a big value, then we get smaller as the search begins. As the surge goes on, the temperature decreases. Okay.
Is it this from? Because usually we are bringing it from the smaller to big.
No. In simple engineering, we're doing we set the temperature from bigger and then we gradually decrease to smaller.
Okay. Yeah.
Because we are simulating how the metal is cooling down during the metal after the metal fabrication. Okay, after the metal forging, right?
All from hot.
So the temperature is keeping decreasing. Okay. So that is why the T is getting decreasing as the surge continues, okay? And as the T decrease, the this EXP delta T chunk of things will also decrease as well, according to this graph, okay? So because of that, the threshold for taking the negative step and for taking a bad move is gradually decreasing as well. Okay? But in fact, it depends on your implementation. You can actually have another technique to implement the threshold as well, as long as something that is keeping decreasing, reducing the chances of making a bad move, then that's work out as well. Okay. The main idea is that as the surge continues, you allow bad move, that the chances of making a bad move should decrease. Okay, that is the reasoning of the simulated anyway. Allowing bad move in the beginning will allow you to escape from the local optimal. And when you get closer to the end of the surge, you should be very close to the global optimal. As a result, you should reduce the amount of the bad move such that you do not escape from the global optimal. Okay, because you do not want that. Okay, so any questions? Any questions?
But that is as long as there is the domain of the variable x, like the horizontal one, is not from like negative infinity to positive infinity. It must be defined the domain. Otherwise, it will still go on, right?
No, because I'm not understanding.
So I mean, just saying, if x, I mean, if you said that x actually, it can go on until infinity, that the whole column can.
Well, you when you're doing the search, you are limited by the temperature. So the temperature when it goes to zero, the search stops. So the search cannot go indefinitely.
So the whole thing is I have to think in the physical world, right? The making the solar that content, right? It cannot be a bit different, like the T represent time.
We are just using this kind of thinking incorporated in our design only, okay? It doesn't necessarily need to be one-to-one to the metal forging. We are just taking the concept, borrowing the concept, bring it right here only, okay? So anyway, we take I will end the lecture right now because it's already 2:27, okay? Because other cars will be right there as well, okay?